Let's solve a problem that has complex conjugates for eigenvalues and eigenvectors. We haven't looked at one of those yet. So let's consider this 2 by 2 matrix, negative 2, 4, negative 2, 2. And we're going to try to find the eigenvalues. So here we have the determinant of the matrix A minus lambda I. So remember, we just subtract the eigenvalues lambda from the diagonal elements. So we have minus 2 minus lambda, 2 minus lambda. The other numbers stay the same. So we just have this product minus this product. So when we subtract the negative, we end up with positive. Multiplying these together, you get negative 4 minus 2 lambda plus 2 lambda, and then plus 8, and plus lambda squared. So when we look at this, we notice that these terms cancel, and you're just left with lambda squared plus 4. Set that equal to 0, you have lambda squared is negative 4, so you get your complex conjugate eigenvalues of plus or minus 2i. Well, let's see what happens now. Things will look a little different now because we're substituting imaginary numbers into our equations. So remember, we're going to subtract 2i in the place of the lambdas here. So we end up with minus 2 minus 2i and 2 minus 2i. Now think back to the previous examples when we had real numbers. We could easily look at these two rows and tell that they were constant multiples of one another. We know they're constant multiples of one another because the determinant of this matrix is 0. That's how we found the eigenvalues. It's not obvious that these two rows are constant multiples of one another, but they are. They're just imaginary numbers multiplied by one another to get the other equation. So we just, again, get to pick one of the equations to work with. So I picked the first one. So I get this number, minus 2 minus 2i, times the first component, plus 4 times the second component equals 0. I could have easily picked the second row. We get the same thing. All right, so moving this term to the right-hand side, we get the negative of the expression in parentheses. Multiplying through by that negative makes this 2 plus 2i, that quantity times x sub 1. And that's equal to 4y sub 1. Divide both sides by 4. Factor out a 2. Do some simplifying, and you get 1 plus I times x sub 1 over 2. Now, there's an infinite number of solutions. Let's just pick a nice value for x sub 1. Let's say I pick 2. I could pick anything, but let's say I pick 2. If I pick 2 for x sub 1, then the 2's cancel and I'm left with y sub 1 equals 1 plus I. Now, the eigenvector that goes along with this eigenvalue is given by x sub 1, y sub 1. You picked x sub 1 to be 2. You put that there. The y sub 1 value is 1 plus I. And that is the eigenvector that corresponds to this eigenvalue. Now what we want to get used to doing is putting the real parts and the imaginary parts, pulling those apart. So there's the real part, the 2 and the 1, plus the imaginary part. There's no imaginary part to the first component, and we have I in the second component. Then we just factor out the I from this vector. That leaves you with 0, 1. So in the future, when we're solving differential equations, we're going to call this vector A and this vector B. But that's in the future. Now, the good news is when you're working with complex conjugate eigenvalues, we don't have to go through the work we just did to get the other eigenvector. It turns out the eigenvector corresponding to lambda sub 2 equal to negative 2i, the other eigenvalue, is the complex conjugate of the vector we just found above. So not only are the eigenvalues complex conjugates, but the eigenvectors are complex conjugates. So we don't have to do any extra work to find it. The eigenvector that goes with the eigenvalue of minus 2i is just the complex conjugate of the vector we found up here. The symbol here represents complex conjugate. So that just means you take the complex conjugate of each component. The complex conjugate of a real number is just the real number complex conjugate of 1 plus I is 1 minus I. And again, I pulled apart the real parts and the imaginary parts. But that's just something we'll work with when we're solving differential equations. So just as a note to you, and what we're going to be doing, we'll be working with 2 by 2 matrices. So we'll have the cases of distinct real eigenvalues and complex conjugate eigenvalues. Those are the ones we're going to focus on, and we're going to skip problems that have repeated real eigenvalues. So that's what we have to look forward to next time.